this video, we'll be looking at coaxial technology as well as coaxial connectors and cable assemblies. We will be reviewing the following aspects of the topic. What is coaxial transmission? The structure of a coaxial transmission line, connector materials, connector mounting styles, electrical specifications, and the processing methods of coaxial connectors and cable. The term coaxial refers to objects that share a common axis. In geometry, it describes circles aligned along the same straight lines. A coaxial cable is built from concentric layers of material that share an axis. Its structure typically consists of a central conductor surrounded by a dielectric insulator, then an outer conducting shield and a protective jacket. This concentric design allows coaxial transmission lines to carry high-frequency signals with low loss and minimal interference. The outer conductor contains the electromagnetic field, improving efficiency and reducing signal leakage, while the shielding and outer jacket help protect against external electromagnetic and radio frequency interference. Because of these properties, coaxial cables are widely used in applications that demand reliable signal transmission, such as television and radio broadcasting, medical imaging, and data communications. It is important to note that coaxial cables and connectors are passive components. They act simply as conduits for the signal, allowing it to pass through without altering or modifying the transmission in any way. This image shows a cross-section of BNC connectors in a cable assembly. On the left is the male cable connector attached to the cable via a central pin. The shielding and outer jacket are crimped at the rear with a ferrule, ensuring a secure connection and continuity with the connector body. On the right is the female connector. This example is a panel-mounted type with a rear cable connection, although PCB-mounted versions are also available. The female receptacle mates with the male center pin, while its outer conductor maintains a continuous ground path with the connector body and mounting interface. If you look closer, both the cable and connectors share a coaxial architecture. Each consists of three concentric layers: the central conductor, the dielectric insulation, which also includes any air spaces inside the heart of the connector, and the outer conductor or shield, which in this case of the connector is the outermost structure, the metallic connector body. When mated, the male and female connectors form a continuous transmission line, allowing the signal to propagate seamlessly along the cable. The concentric design minimizes signal reflections, optimizes transmission performance, and maintains electromagnetic compatibility across the interface. Cambridge Electronic Industries coaxial connectors are designed and manufactured to provide a durable and reliable connection using high-quality materials across all component parts. Connector bodies are manufactured from either die-cast zinc or machined brass. The body is then plated with nickel or gold, or a combination of both. While there is no electrical difference between these finishes, nickel plating provides a cost-effective, corrosion-resistant hard-wearing coating with an appealing silver appearance. The insulators surrounding the contact pins can be produced from several materials. The most common is PTFE, which is white in appearance. Connectors in the Pathfinder range use TPX, a transparent material that allows light to pass through, potentially offering a guiding aid to engineers working in dark spaces. A third option is PEEK, valued for its radiation resistance, making it well suited for nuclear sector applications. Each contact is precision machined from phosphor bronze or beryllium copper. These alloys have been chosen for their corrosive resistance and strength. Cambridge Electronic Industries typically apply a 10 micron inch gold plating to all contact pins in coaxial connectors. This thicker plating ensures excellent electrical performance and supports a high number of mating cycles, providing long-term reliability and consistent peak performance. Coaxial connectors are available in two genders. Male connectors, also known as plugs, contain a protruding pin as the center contact. They are most commonly cable mounted for connecting to equipment, but some PCB mounting forms do exist. Female connectors, also known as sockets or jacks, contain a receptacle contact where the center contact has a hole or spring fingers. Usually board mounted, so equipment has sockets for users to connect to. They are also available as cable mounted jacks when required. The gender is defined by the centre contact, not by the outer shell, which can sometimes be misleading in connectors such as the SMA versus a reverse polarity SMA. Standard practice is that the equipment or the chassis has the female jack and cables have the male plug. This helps prevent exposed live signal pins on equipment. Coaxial connectors are available for both PCB and cable mounting. PCB mounted coaxial connectors will have a centre pin that either sits on top or goes through the board and solders to the signal trace. The outer shell usually has multiple solder or press fit legs that connect to the PCB ground plane for mechanical stability and electrical shielding. There are 5 main PCB mounting styles. These are right angle, edge mount, surface mount, top entry, and end launch. The right angle is a connector with a PCB through-hole right-angled central pin. The connector body will have legs that go through the board to connect to the ground plane. The contact of an edge-mounted connector is straight and sits on the top surface of the PCB. The PCB then slides between the legs of the connector. The distance between the legs on an edge-mounted connector can differ to suit different board thicknesses. A surface-mounted connector has a centre pin that is mounted to the top surface of the PCB, and the legs tend to be right-angled through the PCB, offering mechanical stability. A top-entry connector has a straight pin that goes through the connector body, and the connector is mounted perpendicular to the PCB. The centre pin of an end launch connector is straight and is surface-mounted to the top of the PCB. Posts go through the board at right angles to hold the connector in place and connect to the ground plane. Cable-mounted connectors are usually available as straight or right-angle mounted connectors. The cable connectors come as 3 separate parts: the pin, the body, and the ferrule. Cable-mounted coaxial connectors are designed to attach directly to a coaxial cable. The centre conductor is either crimped or soldered to the connector's centre pin. The dielectric fits into the connector's body to maintain impedance matching. The outer braid and jacket are folded back and captured over the back of the connector body, and then a ferrule or metal sleeve is then slid over and crimped to provide mechanical strength, shielding continuity, and strain relief. Even though the interface of a cable connector is standard, the cable entry size differs depending on the cable type that the connector is designed for. Coaxial connectors are available with a bulkhead or as a straight connector style. A bulkhead is a partition or wall, and in electronics this usually refers to the equipment enclosure or panel. Bulkhead connectors are designed to pass through a panel or housing wall. The connector body has threads and a mounting nut, sometimes with a washer, which are then secured to the bulkhead. This allows one side of the connector to face inside the equipment for internal wiring or PCB connection, and the other side to face outside for the user cable connection. Bulkhead connectors provide a solid mechanical mounting point. They maintain shielding and grounding continuity through the equipment wall and allow for easy cable attachment and detachment without stressing the PCB or the internal wiring. There are several different formats that coaxial connectors are available in. The most widely used types in the broadcast of video and audio signals are BNC, micro BNC, and DIN 1.2 to 2.3, which is also known as DIN 1023s. The BNC connector is the primary connector used for broadcast transmission due to its compact size and ease of connection. It features 2 bayonet lugs on the female connector, and the mating is achieved with a quarter turn of the coupling nut on the male connector. The name BNC is derived from the inventors Neil and Konchelman, who designed the connector in 1951. Our BNC connectors are available in a range of mounting styles in both 50 and 75 ohm options and support frequencies up to 12 GHz. The micro BNC connector is a miniaturized version of the standard BNC and is also referred to as the HD BNC or ultra tiny BNC. At 51% smaller than the standard BNC, it is designed for high density applications. These connectors are available in 75 ohm options, supporting frequencies up to 12 GHz as standard and up to 25 GHz on selected models. The DIN 1023 connector, introduced in the 1990s, uses a quick-release push-pull mechanism. It is available in 75 ohm options and supports frequencies up to 6 GHz, which is the maximum working frequency for this type of connector. These three connector types are suitable for a wide range of applications, including broadcast, as they comply with the SMPTE SDI standards and the JIIA Coax press standards for machine vision. As more companies adopt these standards in new equipment specifications, the market continues to expand across diverse sectors such as medical, aerospace, defence, machine vision, broadcast, automated vehicles, and manufacturing applications. Other connector types in the coaxial connector range include TNC, N-type, F-type, SMA, SMB, MCX, and MMCX. The TNC connector is a threaded version of the BNC connector and shares a similar interface size. While less popular than the BNC due to its slower release mechanism, it is valued for its secure threaded connection. RTNC connectors are available in 75 ohm versions and support frequencies up to 6 GHz. The TNC connector has been used in a wide range of radio and wired communication applications. The N-type connector is a threaded waterproof coaxial connector invented by Paul Neal in the 1940s. It is one of the largest coaxial connectors with a thread size of 5/8 of an inch, 24 UNEF. Our N-type connectors are rated at 50 ohms impedance and operate at frequencies up to 6 GHz. The F-type connector features a long threaded female interface that mates with a cable-mounted threaded male plug. Commonly used in cable and satellite television, the F-type connector is unusual in that it does not employ a central pin. Instead, the bare cable conductor itself serves as the contact within the female socket. They are available in 75 ohm options and support frequencies up to 6 GHz. The SMA Subminiature Version A connector is a widely used 50 ohm connector with a screw locking coupling that ensures a secure connection and reduces vibration issues. Standard SMA connectors operate at frequencies from 0 to 6 GHz, while specialised models can reach up to 26 GHz. They are commonly used in aerospace, defence and high-performance RF applications, with some designs employing peak insulators to guard against signal leakage. The SMB Subminiature Version B connector is a smaller variant of the SMA and uses a snap-on coupling mechanism for quick connection. They are available in both 50 and 75 ohm versions, with an operating frequency up to 4 GHz. The SMB range is sometimes described as reverse polarity, as the plug features female contacts and the sockets contain male contacts. The MCX microcoaxial connector uses a snap-on interface and is predominantly available in 50 ohm versions. Supporting frequencies up to 12 GHz, MCX connectors share similar interface dimensions with SMB connectors, but are approximately 30% smaller in body size. They are well suited for applications requiring compact, discrete antenna connections. The MMCX micro-miniature coaxial connector is one of the smallest RF connectors available, with a 50 ohm rating. It features a lock-snap mechanism that allows for full 360-degree rotation. Suitable for applications up to 6 GHz, MMCX connectors are widely used in antenna systems for mobile devices, GPS receivers and other compact electronics where space is limited. PCB mounted connectors are soldered to PCB boards in one of three different soldering methods: either hand soldering, wave soldering, or reflow soldering. All connectors can be hand soldered onto the board using the most traditional method of soldering with a single strand of solder and a soldering iron. This process ensures a reliable connection between the connector and the board while placing minimal stress of the connector components. Each connector datasheet specifies the recommended hand soldering temperature and the allowable dwell time that the connector can withstand. Most connectors can be wave soldered, with the exception of edge-mounted types, since the solder wave only applies to one side of the board. In wave soldering, the entire board is passed through a wave of molten solder, securing all components in a single step. The solder temperature can reach up to 265 degrees centigrade, but because the process is very quick, stress on the connector components remains low. Reflow soldering differs in that connectors are first positioned on the board using solder paste, which acts like a temporary adhesive. The assembly is then passed through a reflow oven, where the temperature is gradually increased to a peak value over a controlled time. Since reflow soldering subjects components to higher and more prolonged heat compared to hand or wave soldering, connectors used in this process must be of a special design. The design ensures protection of the insulator, the component that is most affected by heat stress. If a standard connector is exposed to reflow conditions, the insulator may expand, pushing the connector away from the board and resulting in misalignment or unusual positioning. There are three main electrical specifications reviewed by RF engineers. These are frequency, impedance, and return loss or VSWR. Frequency refers to how often an event occurs within a specific time period. The standard unit of measurement is the hertz, which equals 1 cycle per second. A simple example of frequency can be found in the keys of a piano. The sound we hear is created by vibrations within the audible range of the human ear. For instance, middle C produces about 262 vibrations per second, or 262 Hz. In general, the human ear can detect frequencies between 20 Hz and 20 kHz. In electronics, coaxial connectors are commonly called RF or radio frequency connectors. Radio frequencies are typically measured in larger units, like kilohertz, which are thousands of times per second, megahertz, which is millions of times per second, and gigahertz, which is billions of times per second. So far, we've talked about how frequency affects what we can hear, but frequency also affects what we can see. For example, in the quality of the picture of a TV screen. With RF connectors, higher frequencies usually mean faster data transfer speeds. Faster speeds allow TVs and other devices to handle higher video resolutions, the number of pixels that can be transmitted, and the frame rates, how many pictures or frames per second. Some common examples used in video systems within the serial digital interface standards include 3G SDI, transferring about 3 gigabits per second and supports full HD 1080p video. 6G SDI transfers about 6 gigabits per second and supports 4K video at 30 frames per second. And 12G SDI transfers about 12 gigabits per second and supports 4K video at 60 frames per second, or even 8K video at 30 frames per second. From the point of the end user, this means that they can have a larger screen with a better resolution or clearer picture, as the designer has used a higher speed frequency system within the receiving equipment. In electrical engineering, all circuits resist the flow of current in some way. In a direct current DC circuit, this opposition is called resistance. In an alternating current AC circuit, it's called impedance. A useful way to visualize how electrical resistance and impedance work is to compare them to water flowing through a pipe. In a straight pipe, the main factor that resists water flow is the pipe's diameter. A narrow pipe makes it harder for water to flow, just like a less conductive element in a circuit limits the amount of current. If we start adding bends, curves, or sudden changes in the pipe size, the water has to turn corners and adjust its flow. This doesn't stop the water, but it slows it down and causes turbulence. In the same way, the phase of the alternating current, which has a sinusoidal wave-like shape, doesn't simply resist current. Instead, they delay or oppose changes in the electrical signal. When we put it all together, the total opposition the water faces is not just from the narrowness of the pipe, but also from the twists and changes along the way. In circuits, this combined effect is called impedance. The mix of resistance, the straight restriction, and the reactance, the twists and turns. Just like resistance, impedance is measured in ohms. The impedance value is always shown on drawings and datasheets for connectors. This makes it easier to match them with other parts of the circuit, such as cable assemblies. When all components in a circuit have the same impedance, they work together more efficiently. If there are mismatches, signals can be reflected or weakened, which reduces performance. So the fewer mismatches, the better the circuit will work, which is especially important at higher frequencies. When it comes to designing, testing and troubleshooting an RF system, two critical parameters should be reviewed. These are VSWR and return loss. VSWR stands for Voltage Standing Wave Ratio and is a ratio representing the relationship between the maximum and minimum voltages along the transmission line due to reflections. The best ratios are as close to 1 as possible. Return loss is a measure of how much signal power is reflected back towards the source due to the impedance mismatch in a transmission line. It is measured in decibels. A higher return loss value in decibels is better because it indicates lower reflected power and better impedance matching. Both of these parameters are related to the same signal reflection phenomenon seen in RF systems, but relate to different elements of the system. If you are working with and designing RF circuits, it's essential to understand both concepts and how they relate to one another. Both VSWR and return loss are critical parameters for RF systems as they directly influence the signal integrity and overall system performance. Let's look at why each is important. With VSWR, the results show impedance matching. A low VSWR indicates good impedance matching, meaning that the power from the transmitter is being effectively delivered to the antenna or load without excessive reflection. High VSWR values indicate poor impedance matching, leading to wasted power and potential damage to the transmitter. Signal efficiency. A low VSWR means that the most of the transmitted power is reaching the load, ensuring more efficient signal transfer. And minimizing interference. A high VSWR may cause unwanted interference due to reflections, leading to potential issues with signal quality and range. With return loss, the results show signal quality. A higher return loss signifies the less power is being reflected, which is desirable for maintaining the quality of the transmitted signal. System diagnostics. Return loss is often used in system diagnostics to check for issues like mismatched cables, faulty connectors, or improper antenna tuning. A sudden drop in return loss can signal a malfunction or deterioration in the system components. And reducing losses. Minimizing return loss ensures that most of the transmitted power is being delivered to the intended destination, improving overall system efficiency. Each of these electrical specifications can be found listed on the datasheets, drawings and website for all coaxial connector parts. We hope you have enjoyed the information in this video, but if you would like to know more about our range of connectors or cable assemblies or our bespoke services, please look at our website at www.cambridgeelectronics.com.